Hi. So we continue looking at Laplace transforms. So what I'd want to look at in this video is more like a generalized point of view of some function that might appear like that might be written in different ways. So we just look at the general form of it so that we can use it in on various occasions. So there are times when, let's say, you are given your function f of t to be equals to, let's say, its sine. Instead of just saying sine at here, this can be also be written as, let's say, the angle is at plus b. What do we do? Okay, so keep in mind to say this can as well be cos at plus b, like that. So I want to try to go through this step by step, trying to show you what those two are equals to. But of course, I'll just try to use one. Then you can map the steps that I use on, let's say, for sine, map them on map them on for cos. Then you're still going to arrive at a similar destination or at the correct destination. So I'm going to try to use for sine. Okay, you could have used for cos. You can try out for cos on your own. It's still going to work out. Just make sure to say you follow each and every step that I'm going to take. And I'm also going to show you the possible mistakes that you can make when trying to come up with a Laplace transform of this particular function here. Okay, so now if you go to the Laplace transform tables, you're going to find that the the Laplace transform of this same function that we have here, which is sine at plus b, it is equals to, okay, it is equals to something that appears to be a bit complex, but I'm just going to write it here in advance so that we have a picture of what we are looking for. Okay, so this is supposed to be equals to s s sine b plus, okay, that will be plus a cos b, then divide by, um, we're dividing this by s squared plus a squared. So this is what we're expecting to get from that. Okay, so of course I'm going to use integration by parts, and we just have to be patient here. So I'm going to say um, the Laplace transform of this function here, which is uh, sine at plus b. Okay, this is equals to, we are evaluating our improper integral from 0 to infinity, and we are saying it's sine at, okay, um, sine at plus b, then that to be multiplied by e to the minus st dt. Okay, so now this method that I'm using is integration by parts. I could have used a shorter method, but I just feel like using integration by parts for now. But I also try to show you the shorter method of coming up with the Laplace transform of this function. So what it is here is that, of course, I'm trying to avoid the shorter method because it um, it might tempt you to do some substitutions when you're not supposed to. So let's just go ahead and use the integration by parts. So remember the formula for integration by parts is, we are going to say integral of u dv is equals to uv, uh, minus integral of v du. Okay, so in this case I'm going to say my u is equals to sine at plus b, then my du is just going to be equals to, this is just going to be equals to a, when you differentiate the angle there with respect to t, that would be a cos at plus b. Then my dv is equals to e to the minus st dt. Then my v is equals to minus e to the minus st divided by s. I believe we are now familiar with that. So this is going to be equals to So this is going to be equals to, so I'll put this, that will be u by v, that will be minus our u, which is sine at plus b to the e minus st. That will be divided by s, evaluating from 0 to what, to infinity there. Then that will be plus, because I'm supposed to say minus, but because of this minus that I have, there's going to be plus. That will be a divided by s. Then this will be integral from 0 to infinity of cos at plus b multiplied by e to the minus st dt. Sorry, there is a dt here, like that. Okay, so now here is where you can make your first mistake. That is if you take this to be 0, because with the fact that you have a sign. But try to check this out. If you substitute for, if you substitute here for where there is t, you put where there is t, you put infinity. This is just going to be infinity. But if you put infinity for this one here, you observe that this function compared to this function which is e to the minus st is approaching 0 faster compared to this one. Hence it's going to be 0 when you substitute with what, with infinity. But if you substitute with 0, okay, because of the presence of a sign, you might quickly be tempted to say, okay, it's also going to be 0. But remember to say, if you put 0 here, this is going to be 0 multiplied by a, that will be 0. Remain with what, remain with sine b, which is this b that you have here. Okay, so let's see how this one can be written now. So this one, when you put infinity, we observe that you're going to get a 0. That would be minus, so it will be like infinity. When you put infinity here, so substitute infinity, then minus, substitute 0. We observe to say when you substitute infinity, we get what, we get a 0, because no matter what we get here, regardless of whatever it is, bigger, is smaller, comparing the behavior of this function and that function, this one goes to 0 faster compared to this one. So we get a 0 for infinite substitution. Then if you substitute with 0, you get minus, so that's going to be minus sine, that will be sine b. Okay, sine b divided by that s there. So you observe that for that part, it just ends up to be what, just ends up to be equals to positive sine b divided by s. Okay, so we still have this part, which is plus our a over s, then the integral from 0 to infinity of cos at plus b e to the minus st dt. Actually, this method is even much straightforward as well. Just that I was somehow thinking I'll have to use the addition and subtraction formulas, but it appears I don't have to. I was thinking of breaking this one down, but I feel the addition and subtraction formulas from trig identities are only going to work for the other method, which I'm going to show you as well. Okay, so now I can use integration by parts for this part. So I can leave this one the way it is. We are done for that one. So this one is just going to be, I'll let my u be equals to the trig function, which is cos at plus b, meaning my du is going to be equals to minus a sine at plus b, then of course dt there. Then my dv is equals to e to the minus st dt. Then my v is equals to minus e to the minus st divided by s. So now this is equals to the sine b divided by s plus a over s, then I'll put some brackets there. So that would be u by v, that would be minus cos at plus b multiplied by e to the minus st This minus here, I've already put it, it's right here. Okay, so that will be divided by s, which is this s that I have here. Then I'm still evaluating from 0 to positive infinity. Then I'm still going to subtract here because multiply the v by the du. This negative times that negative becomes positive. So you still maintain the negative from the formula for integration by parts. So that would be from 0 to infinity of and by the way, there are still some constants that I can pull out, which is the a divided by the s, this a here and this s right here. So that would be from 0 to positive infinity. Then that would be sine a plus no. So wait. So that would be sine at plus b multiplied by e to the minus st dt. Okay, we are getting closer and closer to the answer that we are looking for. Okay, so you understand to say this is going to be very useful when you start doing some when you start bringing on some examples that have some actual values. In terms of a there's a value, in terms of b there's some particular value as well. Okay, so now this is just going to be equals to I'll have my sine b divided by s. Okay, so evaluate for this one. One thing that you observe is that if you substitute with infinity, you're going to get a 0, which is something that I've already explained in the like one of the previous steps. Then if you substitute with 0, you're not going to get a 1, you're going to get cos b, because if you put 0 here, that is going to be a multiplied by 0, that would be 0, so you remain with cos b. But because there's a negative, it's going to be positive, so that would be more like a over s multiplied by cos b divide by s. That is just for this part. Okay, then you are going to say minus this a multiplied by that a there. That's going to be a squared divided by s becomes s squared of this one here. Okay, which is our which is 0 to positive infinity. Then we say sine um, that's going to be sine a t plus b, then by e to the minus st dt. Okay, so remember to say initially this is what I was looking for. This is just more like the Laplace transform of that one there. So what I would do is that to simplify my work, because the way this was written is just more like you are saying you're looking for the integral of the improper integral of let's say from 0 to infinity of sine sine at, okay, plus b e to the minus st dt, and we have found that this is equals to everything that I have here, okay, including this one here. So let me just write this one as what? Let me write it as in for simplicity purposes. Okay, remember this is equals to that. So in place of this one, I'm going to use the letter in. Okay, so meaning I can say my in is equals to what I have here, which is my sine b divided by s plus a cos b divided by s squared minus a squared over s squared. But remember to say I can write this as what? As in. So what do? Correct the like terms. So this is going to be in open bracket, or maybe before I even do that, that would be plus a squared over s squared by in is equals to, this is still, I'm going to leave it as sine b there divided by s plus that would be um, a cos b, then s squared, like that. Okay, then I can now factor out the in, which is going to be 1 here, then that would be plus a squared over s squared. This is equals to, I can make this as a single fraction. Okay, I can put the s squared, which is the common denominator, so that would be our s squared. So s into s squared will have s, so that would be s sine b, then that would be plus a squared into a squared is 1, so that would be a cos b, like that. This is looking beautiful. Okay, so now this is like in, then you make this a single fraction as well, like this part, make it a single fraction. You observe that what is common there on the denominator is what? It's s squared. So 1 into s squared is what? Is s squared plus a into this s squared into this s squared is a 1 multiplied by a squared, that's going to be a squared. So this will be equals to s sine b plus a cos b divided by a squared. You observe to say we can cancel out this one and we can cancel out that one. If you're wondering why I'm canceling out, it's just more like you do the cross multiplication. But let me just, if you do that cross multiplication, um, or maybe not even talking about cross multiplication, guys, let me just write it this way. Let me multiply everything here. Let me multiply everything by what? By s squared over s squared plus a squared, so that I just remain with in on this side, which I believe is something that you are very familiar with by now. Okay, that's our s right there. Okay, so now you observe that if or when I multiply this one by that one, the s squared cancels out, the s squared cancels out, the s squared plus a also cancels out, so you remain with what? In is equals to. So now you observe that if you multiply this side by what you have here, this will cancel out and that one will cancel out, which is exactly what I did. So that's going to be s by sine b plus a cos b divide by that will be divide by the s squared plus the a squared. We have it. This and that are the same. So that's simply how they came up with that one. And you having known this right now, you don't have to go through the same process again, like trying to integrate by parts when you're given a function, like some example that you're going to do in the next video. Let me give you a sneak peek, which is a sine 3t plus 2. We are going to do this example in some next video. Okay, so we can just map everything that we have here. We observe to say this is just a and that is our what? That's our b. So it's just a matter of substituting, and then we are going to have our answer. Okay, so this is how you can come up with the solution for this one by using integration by parts. Well, let me show you something that I feel is quick. Remember, of course, it's quick, but it just requires you to remember something. But remember, like, think integration by parts, I didn't really have to stress myself thinking about some identities or something. I myself, I usually forget them sometimes, unless those that are very basic. Okay, so there are these trig identities we call addition and subtraction formulas. Um, Let me pick for sine, because I'm dealing with sine. I'm going to pick for sine. So remember to say if you have sine, let's say you have sine a plus or minus b. This can be written as sine a cos cos b, then that would be plus or minus cos a, then sine b. So here I have that. Okay, so I have like uh, sine at plus b. This is going to be equals to sine, this will be equals to sine at, okay, then cos b, then this will be plus cos at multiplied by sine b. Oh, wait a minute, I've used uppercase b. I'm supposed to use the lowercase b because that's what I have. So I'll put b there and I'll put b there like that. So now what it is that we have to remember that we're just looking for the Laplace transform of this one, and remember the linearity property. Remember that Laplace transform is linear. So what I can do is that I can say I can write this as looking for the Laplace transform of sine at cos what? Cos b plus the Laplace transform of uh, cos AT multiplied by sine B. So look at what you have now. This this right here, okay, is going to be treated as a constant in this case because of the angle that we have. Unless if there was a here and there's an a there, that could have been a different case. So it simply means I can bring it outside and say cos b, okay, cos b multiplied by the Laplace transform of sine at plus. You do the same for this part, which is going to be sine b multiplied by the Laplace transform of cos at. Okay, so the reason why I was avoiding this one at first is because someone might be tempted to feel maybe you have to do something for the cos b as well, but I'm just treating it as a constant for now. But remember, in the previous videos, in the previous video we did we showed how to come up with the Laplace transform of sine at as well as cos at. That is by using the Euler's formula or the Euler's equation. But you can also use integration by parts, and we ended up with, we say the Laplace transform of this one, it was equals to a over s squared plus a squared. Then the Laplace transform of cos at, we ended up with s over s squared plus a squared. So this is just going to be equals to, we put the cos b, okay, multiplied by the Laplace transform of sine at, which is a, okay, um, which is a over, that's a over s squared plus a squared. Then that would be plus sine b, okay, multiplied by the Laplace transform of cos at, which is s over s squared plus a squared. Okay, so now one thing that you observe here is that the denominators are the same, so they are common. So I can just write this as s squared plus a squared. Then I can write the numerators the way they are, which is a, which is going to be a multiplied by cos b, then plus s by sine b there, like that. And if you observe, this and that are just one and the same. It's just like I've just swapped this one and that one, but of course you can still swap them again. That's still going to give you one and the same thing. So that's how we come up with the Laplace transform of such a trig function. Okay, so when you do some questions, I will not have to go through these steps again. So make sure to say you watch this video before you watch this video to the end, and thanks for watching to the end. So that it will be very much easier for you to understand any other question that I do that are related to this, because I'm not going to use integration by parts. Thank you very much for watching, and we'll catch you in the next one.